And I'll record it, because why not? So there are three questions on here, and if you were, So there are three questions on here, and if you were thinking, you probably realize that since there are three factors involved in nucleophile strength, there was probably one example of each, so it's just a matter of figuring out which one was which. The first one is fluoride ion versus bromide in ethanol solvent, so you need to know what those things look like. So ethanol is CH3CH2OH, and the important thing about it is that hydrogen attached to an electronegative element, which means this is a protic solvent. The book would refer to it as a polar protic solvent, but it's impossible to have a non-polar protic solvent because any protic solvent can do hydrogen bonding. And we are talking about F- and Br-. Right. So in a protic solvent, chances are good that the most important effect is the solvent effect in this case. And what you need to recognize is in a protic solvent, anionic nucleophiles are solvated pretty heavily. And the smaller they are, right? Fluoride is a fairly small ion, bromide is a fairly large ion. The smaller the ion is, the more heavily it will be solvated. So what we're trying to do is compare the strength of the ion dipole force. The ion dipole force, like most of the others, is controlled by Coulomb's law, so the force is equal to some constant times Q plus times Q minus over D squared. So as the charge increases, the force is going to increase, which is why anionic nucleophiles are affected a lot by the protic solvent, and the distance. So this is the key term, right? The key term here is the distance squared. The shorter the distance between the solvent and the nucleophile, the larger the force of attraction. And fluoride forms a double solvent shell. So if you want full credit on this, you had to tell me that fluoride formed a double solvent shell, and then you had to draw a picture that shows that anion, fluoride, right, surrounded by the partial positive hydrogens of the ethanol. And I don't know how many you needed to show, but some, so that you get a solvent shell here. But then that introduces enough polarity, because these oxygens all have partial negative charges on them, that you can get a second solvent shell where hydrogens in the ethanol now kind of bind to the partially negative oxygens of the first solvent shell. Right, so you get a second solvent shell around here. That causes that to be pretty stabilized. And if fluoride is surrounded by these ethanol molecules, it has trouble getting out of that solvent shell to interact with a carbon of a substrate. By contrast, bromide ion is a pretty large ion, so it is surrounded by your ethanol molecules. I think that's propanol. But the distance here of separation is much larger, which means the force of attraction is quite a bit smaller. And because that force of attraction is quite a bit smaller, bromide has an easier time escaping, right? We have these partial positives on the hydrogen. Right? So that larger D decreases the force. So that's page 1. Right? That's the first example. Part B, you're working with triphenylphosphine or trimethylphosphine versus trimethylamine. So that's phosphorus with 3 methyl groups attached, and a lone pair, versus nitrogen with 3 methyl groups and a lone pair. Right? These are neutral nucleophiles. And they're in different rows, which means that the big factor is going to be polarizability in this case. And the benzene is the solvent. Benzene is a non-polar solvent, so it has no effect whatsoever. It's just the aromatic ring. Right? There's going to be no solvent effect for neutral nucleophiles anyway, because you don't really have a strong ion dipole force like you do for the anionic nucleophiles. So what we need to do is we need to pick a substrate. Let's just take a simple substrate like iodomethane. There's no reason to have a more complicated substrate than absolutely necessary. And what we're looking at here is the unoccupied orbital, the LUMO, that electrons have to donate into in order to cause a reaction. So when we have trimethylamine, right, we've got a fairly small HOMO orbital on the nitrogen. I'm just going to show them as dots. Our lone pair is in that fairly small HOMO orbital. So we've got to get this nitrogen pretty close to that carbon in order to get overlap. And in case, if we don't have that overlap, then we can't actually cause a reaction. Whereas in the case of the larger triphenylphosphine, or trimethylphosphine, sorry, I keep saying phenyl, right, it's the same LUMO orbital that we're trying to donate into. But now, since the phosphorus has a much larger HOMO orbital, we can donate electrons in at a much larger separation. You don't want the nuclei to get too close, because once the nuclei get too close, they start repelling each other. So here you can start breaking that bond, right, because there's a node here. So if you donate electrons into that LUMO orbital, you're going to start breaking that carbon-iodine bond. You can start breaking that bond without the nucleus having to get too close. So the carbon doesn't really know that there's this large positively charged nucleus approaching it. Right? At that same internuclear distance, if you had the nitrogen, this picture wasn't really necessary, but at that same internuclear distance, right, we've got that HOMO, you would not actually get any overlap at all. This minus sign, by the way, is the sign on the orbital, on the wave function, right? So there's no overlap here. And you could have picked any substrate you wanted, but iodomethane is a nice simple substrate. So since you've already used solvation and polarizability, probably the next one was going to be basicity. We're working with anionic nucleophiles, and we're comparing CH3S minus with CH3O minus, I think. Double check and make sure that was actually the question. Yep. And the solvent is THF, tetrahydrofuran. Again, it's a nonpolar solvent, which means it doesn't really solvate either of those anions particularly well, so you're going to be working with base strength. So you're comparing the pKa of CH3SH to CH3OH. What is the pKa of that thiol hydrogen? Anybody? No? Nobody? You're supposed to still know your pKa values. No? Come on, somebody has to know it.
The pKa of the SH is 12.
12. And for the OH?
15.
So which one is the stronger acid? What's the correlation between pKa and acid strength? Is it a lower pKa is a stronger acid, or a higher pKa is a stronger acid?
Lower.
Lower. So this is the stronger acid. That means that's the weaker base. And methoxide is the stronger base, which means methoxide is going to be the better nucleophile. It's a better base and a better nucleophile. Right, so you had one, right, part A was solvent effect, part B was polarizability, part C was the base strength. And you probably knew that you were going to have one of each, at least if you're pretty smart at anticipating what I'm likely to add.